Hello, I'm Chen Yu. I'm from School of Science and Engineering at University of Dundee. Today, I'm going to share my work, generating chest radiology report findings using a multimodal method. To help everyone better understand my work, I'll start by giving a brief introduction to radiology. Here, we have an example from the MIMIC6R dataset. It's the same dataset I used for my experiments. On the left, you can see the radiology image. It includes both the frontal and lateral views. On the right, you can see the radiology report. It consists of three main parts: the indication, the findings, and the impression. The indication section describes the referring clinician's reasons for requesting the CSR and relevant aspects of the patient's history. The findings section contains observations based on the radiology image. The impression section contains clinical diagnostic information. Our main task in radiology report generation is to produce the findings section of the report based on the radiology image. You must want to ask me a question: when are we doing this and what's the significance of it? The reason is that automatic radiology report generation from chest X-ray images can improve clinical efficacy and efficiency, while also elevate radiology's pressures. Many researchers are working on this, but most existing methods rely only on visual information from images for report generation. But we propose a multimodal method. We use both the images and the text describing patient's history to generate the report. This is my method. The model architecture comprises three primary components: an image encoder, a text encoder, and a text generator. The image encoder focuses on extracting visual features from radiology images. Simultaneously, the text encoder focuses on extracting textual features from the indication text. The orange part is just our core technique. The text generator uses a transformer-based architecture to generate the final report findings. It's fine-tuned, conditioned on the extracted visual and textual features. We use two image-based methods as our baselines, so we add the orange part to the baseline methods and follow their image encoder and text generator. Then I'll introduce the three primary components respectively. For the indication text, we use PanMyBird to extract the textual vectors. PanMyBird is a variant of BIRD, fine-tuned on biomedical text from PanMy abstracts. BIRD is a multi-layer bidirectional transformer encoder based on the original transformer implementation. As for the image encoder, then employing R2GN as the baseline, follow their method. We use ResNet 101 CNN, a convolutional neural network pre-trained on ImageNet to extract the visual features. When employing CVT2 distill GPT-2 as the baseline, following their method, we use the convolutional visual transformer as the image encoder for visual feature extraction. Convolutional visual transformer combines convolutional neural networks and visual transformers for image processing tasks. To achieve radiology report generation conditioned on extracted visual and textual features, we firstly concatenate these extracted features to integrate both visual and textual data. Then using R2Gen as a baseline, we follow their method to incorporate their specifically designed memory-driven transformer. The concatenated features are firstly fed into the encoder of the transformer, and the output from the encoder is then fed into the decoder. Then employing CVT2 distill GPT-2 as the baseline, we follow their method to use distill GPT-2 to generate radiology reports. It's a light version of GPT-2, which is a large transformer-based language model designed for natural language processing tasks. We evaluated our method on MIMICS-R and IUX-ray dataset. MIMICS-R is the largest public radiology dataset. It consists of 377 and 110 chest X-ray images and 227 and 835 radiology reports. IUX-ray dataset contains 7,470 chest X-ray images and 3,955 radiology reports. To understand the matrix, firstly I'm going to introduce a labeler tool. We use textbook labeler to label a generated text and the reference text with 14 different categorical variables. These labels are assigned different values. Label 1 indicates that the label was positively mentioned. Label 0 indicates that the label was negatively mentioned. Label -1 indicates that the label was mentioned uncertainly. Label missing indicates that the label was not mentioned in the report. We use NLG matrix and clinical efficacy matrix to evaluate radiology report findings generation. The NLG matrix assigns the similarity of generated text and reference text by analyzing the overlap of n-grams, and it includes blue 1, 2, 4, 2, and red L. Clinical efficacy matrix. As for clinical efficacy matrix, we firstly use checkboard to label text with 14 labels. The labeling scheme is designed only for MIMICS-R. The precision recall and F1 scores are used to evaluate performance based on the values assigned to these 14 labels. These are our experimental results on MIMICS-R dataset. We can focus on Blue 4 scores and F1 scores, as these are the most comprehensive indicators. We can see that our Multimodal R2Gen and Multimodal CVT2 distill GPT-2 have outperformed the baseline methods on our matrix. In indication, our Multimodal CVT2 distill GPT-2 has outperformed all the other related work on our matrix. This table compares our methods and our related work on IUX3 in terms of NLG matrix. We can see that the CMM method outperforms our method, and we notice that the improvements achieved on the MIMICS-R dataset were larger than those on the IUX3 dataset. The difference is because of the smaller size of the IUX3 dataset compared to MIMICS-R, resulting in greater challenges in model training and inference on IUX3, and consequently smaller improvements. These are the references. We use an example case to illustrate the effect of including indication text, comparing its radiologist-generated findings with those generated automatically using the proposed multimodal and baseline methods. This is an example of a chest X-ray image from the MIMIC-SSR test dataset and its associated radiologist-generated indication and findings text. These are the generated findings using the baseline method AutoGen and our proposed multimodal AutoGen. The multimodal methods comment on a clinical observation at elasticity as requested in the indication. AutoGen method incorrectly predicted pneumonia and enema, but our method didn't. These are the generated findings using the baseline method CVT2 distilled GPT2 and our proposed multimodal CVT2 distilled GPT2. Our multimodal methods comment on a clinical observation at elasticity as requested in the indication. The multimodal methods more successfully predict text that doesn't contain clinical terms present in the expert label site. You can see the text in bold. These are the observations from the illustrated example I introduced just now. In conclusion, we have proposed a multimodal method for generating radiology report findings text. We instantiated this approach by extending two baseline methods, and the experimental results after performed the baseline methods on two public datasets across all metrics and demonstrated improvements through the incorporation of indication text.